DGX, let's say, with 8 GPUs. So that the data can be 50 gig distributed across the 8 GPUs, and you can build one massive model where the data does not have to fit on each individual GPU. Because GPUs only have 16 gigs of RAM. You would say, oh, that's small data, but actually to train on 16 gigs is still a significant amount of work. And you will not be able to train 1,000 models to get to the best feature engineering pipeline. So there's a compromise today that if you want to have many models evaluated, then you can't train them in a way that is too slow, right? You just can't have it both ways. Unless you have a 100 DGX cluster, it's not realistic for most people. So we recommend going to something like 5 million rows or whatever it is for your problem, so that you can run overnight, get good results, and then draw conclusions from there. Multi-user and data connectors, that's the enterprise feature that we're working on. So having Hadoop connectors, database connectors, having security, you can log in. When you log in, the system knows who you are, and then you also have a Kerberos token, and it knows what you have access to. You get only the certain data sets you're entitled to see. Your colleagues can use the same box, but don't see each other's data, and so on. That's all coming next quarter. And then a little bit more on time series. We already have time series support in there, so we do causality, conserving, machine learning if you want. We're not cheating by looking at the future and saying, oh yeah, now I know what to do tomorrow, because I already saw it. No, we're only looking at the past. But we're not making all the lag features and all the cumulative sums and so on automatically yet. That's in the code base, just not enabled. So that's a little bit more work for us to do. The user-defined recipes, UDRs, as I guess we can call them now, they would be very useful, right? If you can just say, oh, what about random forest as a model, because I like random forest. That's the only thing you want to change. Or you want to change your loss function, or you want to change your the way how you do cross-validation. You know it has to be this way, and it can't be done any other way. Well, that sparking mod, as I mentioned earlier, that will be the big one. So if you go to docs.h2o.ai, you'll get all the information you'll ever need for anything. Like it will tell you how to install Driverless AI on your laptop. It will tell you how to install it on all the cloud vendors. It will tell you how to install it in NVIDIA registry. If you have DGX, you have it in the registry of NVIDIA. It will tell you all what about the settings for the knobs. When you start Driverless AI, there's a bunch of settings. This will explain it. So I think we'll get to this right now. So who has it up and running already? Who cheated and clicked a little early? No. All right, let's see. Well, I didn't. Okay, so does anybody still have problems getting this up and running? Only a few? Okay, perfect. So actually, it looks like we're good. Only one person's a problem.
Let's see.
That we call a statistical oddity. All right, so let's scroll down and agree with these terms. I'm sure you read it. Did you see the typo somewhere? There's one extra word, H2O here. Yes. That is there. We'll fix that. Release. So H2O.ai or H2O, doesn't matter, just some password. That is to make sure that you know who you are, no one else knows who you are. Now you need to have a license key. That you get from the instructions here. So you copy paste this blob, every single character here, copy paste that over. Okay, so go back to the quick collapse instructions and copy paste that piece. It's just one long string of some garbled characters. That's your private key. That goes into this product, right into the GUI that it says enter license at the top. At the very top, you paste it in. Don't paste it in the bottom, paste it in the top. If you have an email with an actual license that you asked for earlier, then you can use your own license, because that one is tied to you as a user, which gives you maybe more permissions or something. In this case, I think the only benefit you get is if you have problems, you can tell us who you are and we'll be able to identify you. But for now, this is fine. Like you just use whichever license you want. But if you go home, for example, you have to ask us for a license to get one. And you can ask for one, you'll get one for free, right? 30 days or something, no problem. We want you to give us feedback. So you save this license key, it should go away. And now you're in a good mode. Nothing is in there yet, but we're able to start. Who is ready at this point?
Yeah.
Perfect. Let's do this. Let's start with our data set. And let's go to the data folder. So right now you can still go into every folder in that box and try to read plain text files that somebody wrote. We're going to make that more secure and not allow you to see everything. Right now we give you full access to your own box. But you could argue that someone else could do the same thing, so it's not yet secure. And you know that, it's just not yet finished. So go to data, go to Kaggle, and then go to credit card. And you will see the path at the top. Get the training data, and say import at the bottom. The mouse has to go up and down a few times. If you don't know where to go, just go up or down. And then we'll add another one that's called test. So this is a good principle. You have two data sets, and if you give us both, we will never look at test, just to be frank up front. We will not use it. Even if it's a Kaggle problem, we will not use the test set unless the recipe shouts that out. Right now we don't. Right now what we do is purely training on train. So this 18th position earlier was training on train only. No test set, no distribution checker, no categorical agreement checker, no anything. No missing values, like imputation based on the global, this and that, nothing. There's no secret tricks. When we get to test set, it's the same results as if you don't get to test set. But still, you have it here, and we can actually pass it, and then at the very end, when the model is done, it will tell you what the score is on the test set, if it has a response in it. If it doesn't have a response, you'll just get the predictions for it, and you also get the munched test set. The munched test set is the test set that has the new features added to it, and the bad features removed, if you want. So we make the good data set for you out of the data that you have. That would be useful for further training if you want to, or whatever you want to do. So if you use this model, then we can do the scoring, but you can also refit outside. So we'll give you a transformed training set as well, which has out-of-fold created engineered features that are not overfitting but still valuable. And the features in the training data set that got enriched are smarter than just, let's say, a lookup table or something like it would be done in a test set. So they're doing batch-style munging to give you an enriched data set that's better than a row-by-row transformation. So actually get a good data set out of this process. The training set that's enriched, you could actually throw this into another machine learning tool like H2O.ai and train more. But if you transform
a lot of people,
the training set as if it was a test set, row by row, you'll actually lose some information. So just to be clear about that, it's a small little distinction that the act of turning a training set into a better training set has to be done on a full batch style, all at once mode. It can't be done row by row. But the test set is always done row by row because it's like a real-time streaming scoring system, right? So there's a differentiation between transforming training and testing data. So if you're ever confused, ask us and we'll write a blog about it. We may have not done that yet. So you click on train, it will show you visualize or predict. Let's do visualize real quick. And this is now telling this internal viz server, hey, here's a data set. Find me the outliers, find anything that's unusual, find anything that I should know about, and show it to me. That's for the top part. The bottom part is always shown. It's basically some kind of overview of your data, but not just like a row by row printing of the numbers, but some kind of meaningful way. So you can look at only spiky histograms, for example. I'll show you something that's spiky. There's only one, because there's no other spiky histogram of anything against anything. Everything else is not spiky. It's good to know. Sometimes you'll see something unusual in here. And I think Leland is going to talk about this tomorrow. So you'll go to his talk and you'll hear more about the things that he's written down here from his own words. Okay, if there's people who couldn't open the GPU lab because it ran out, we have too many people attending, there's another one now, a CPU version, which is basically the same. It doesn't matter how you run the CPU or GPU is fine. If you don't care about the speed right now for the small data sets we're doing. So this is the automatic visualization. So that's nice. You can look at outliers. You'll only see things that are actual outliers. See, there's some points here that are interesting. The dot plots actually are fun because they're dropping the points exactly where they belong. It's not like a histogram that you have to make a same width bar somewhere. No, you're putting the point where it belongs. So this one is definitely some kind of outlier you should know about, and so on. It only shows you the relevant stuff, so that's nice. Okay, so let's build a model. Let's go to experiments and say new experiment. You can also do this from the data thing. Instead of visualize, you can say predict. Then you pick the training data set as a training data set. And you pick the test data set here as a test data set. Just for later insights of how well we're doing. And now you have to select the target column. That's really all you have to do. And I will pick the last one, which is the chance of me defaulting next month is what I have to predict, basically. But this actual response has two levels, as you can see here. It has two uniques. So there's a yes and a no, or a 0 and a 1. And this says whether the person will default next month on their payment or not. And that's what we're going to memorize now in terms of a model that kind of makes the best guess, given a person, will that person default next month. So this is a credit card default prediction model, binary classification. We can leave the rest as default, so there's no columns to drop. If you knew that there's some columns in there that you cannot have, then you can drop them, right? Then the model will never see them, as if you never had them. If you have an issue where the rows are not identically distributed and not from the same distribution, and that means that they're also independent. So they could be from the same distribution, but they could be still dependent on each other. Then you would have to say, wait a second, I want to split the cross-validation faults where the same people are in the same fault. So I'm not cheating. I'm not cheating as in that example earlier. And that fault column you can provide. And here we have Mark Landy, by the way. Glad to see him. He's the guy I mentioned earlier in the other talk about the person that brought data science to the company was basically Mark. So hands up for him. If you have any questions about data science, he's very knowledgeable about all these little pitfalls. He has had many presentations about that. You should read his slides. They're very good. And there's also a weight column, and they all have tooltips. If you don't know what's going on, if you look at the tooltips, the weight column tells you the observation rate. Each event, each row has a weight. If you want, you can provide a column that has that number. So now I will say go, but first I'll pick a different loss function for fun, like a log loss. You can do whichever one you want, but we also have a GPU here, so we can enable it, or we can disable it. If you click on the reproducible, it will just make the experiment be the same every time you run. That means if you want to know that it's going to be the same because you have a presentation tomorrow and you want your boss to see what's running live to be good or something, you can try that it works with the reproducible on, and then tomorrow it will be exactly the same. If you don't do it, then it will just be different. Now, you'll still get the seed that was used the experiment. At the end, you will know which seed it was. So if you have a Python script, you can rerun the experiment with that seed. You'll get exactly the same results. But from the GUI, you don't want to type in seed, so you just made it like on or off. And this is the classification problem. I could say no. I want to make a regression problem out of 0, 1. It's like my age. I want to predict how old I am or something. It's not really a yes, no. I know better this is a real age, but it's kind of weird if it's 0, 1, right? It's binary. So I think it's not a classification. It's not a regression problem. It's classification. So everything was auto detected just fine. I'll take the log loss and I'll say go. Now this is running. As it's running, you'll see that it does something at the top. It says tuning backend. Oh, did something already. And now it's training 0 out of 8, 2 out of 8 parameter tuning model. So it's doing some parameter tuning at the beginning. First, it figured out the backend, which means it figures out if GPU works or GPU has a problem, and it runs on the CPU. And once it knows how to run, it will do some preliminary tuning, which is basically saying, figure out how to transform my response if it's a regression problem. Do I need to do a walk transform or square root transform or something? And if it's a classification problem, like in this case, it won't have to do that. It can just tune the XGBoost parameters in this case. So it tune different depth, different column samplings, the row sampling rates, and so on. The standard stuff you would normally tune. And it already did that. Now it says it's starting with the feature engineering. So it has like a good model that knows the data is reasonably well understood by this model. And now that we have a model, we'll keep the model the same. So the model parameters don't change, except the number of trees. So we do early stopping. Once it starts overfitting, we stop. We don't fix the number of trees. So even though everything else is fixed, we still let it converge until it's optimal, as judged by a out of fold holdouts. So it's all fair. We're basically doing early stopping on our tree building, and now we're building lots and lots of trees. Each model can have up to 1,000 trees or so, and we're building hundreds of these models. That's why GPUs are useful. Now this is a very small data set with 20,000 rows. So if you're saying, oh, my CPU is actually faster than a GPU, yes, that's because it has to go over the PCI Express bus back and forth just to put in 20,000 rows and then run the algo in like 10 milliseconds or something. So don't judge this by small data, please. You can judge the accuracy, but even that, we don't have a small data recipe yet. So if you have a 100-row data set and you say, oh, look, this statistically is like my toy case, we might not do that well on that. Although, as Lee pointed out the other day, he had 2 Gaussian blobs and made the data set. It's very difficult not to overfit, and we did not overfit. So we do use reusable holdout and other principles to make sure they're not overfitting. So in this case, you'll see now it's running 2 minutes, 11 points, iterations down the line. Who sees something like this on their screen, just to make sure that we're all following here? Okay, great. Now we can tell a little bit more about what's going on. So the top sections are just giving you an insight about the progress, how many models so far, so 41 models, and 764 features have been engineered and tested. The left side is the same as what you typed in at the beginning. The right side is also what you said at the beginning, except that there's CPU and memory and GPU usage indication on the right. There's also a trace. You can click on the little trace button, and you'll see basically what's happening. So each green thing is a GPU model, each gray thing is some kind of method call. You can mouse over and you see what's going on. It's basically some kind of a real-time tool that gives you an insight of what's running. The red stuff is feature engineering. So every so often it makes some new features, then it builds a bunch of models, and then it builds new features, models, and so on. This is how you figure out what features are good. And in the bottom left, you see the chart with the performance metrics as judged by always out of fold. So we're not showing the metric of training on the training data. We're not scoring a model on the training data and saying, look how low the loss is. We're only showing you validation scores. So every score you ever see will be an out-of-sample estimate of how it's doing on the unseen data. But it could be done either with like a third of the data or a fourfold or something. It's not consistent how exactly the number is obtained. It's just the best estimate. Even if it's a 2/3, 1/3 split, We're still doing many, many scoring runs on samples of those data sets to give this reusable holdout principle a good run for its money, right? We're not taking one number, making many numbers and giving it a mean or whatever we compute from. So it's a good number. That's all I want to say. It's not just one test score somewhere on some validation split. It's a good number. It's what we think this is how well your model does so far. And if you look here, we're down 30 iterations of this genetic algorithm. If you want to know more about the genetic algorithm, you can mouse over and explain everything. There is a variable importance chart. Here you can see that the features are pretty widely ranged. So it is pay times pay. So these are two different pay amounts are multiplied. There's a cluster distance after we segmented these three payment columns into clusters. And then you compute the distance to cluster one. This could be the rich people or the poor people, whatever you want to call it, right? So you're supposed to not make these judgmental decisions in credit scoring or discriminate against people. This will tell you why. This is not a neural net that says the weight was 7.3. This is telling you really what is the feature. So we're reasonably well interpretable with this. And there's frequency encoding, cluster target encoding. So we have first we cluster the data, then we make groups, we say this in each cluster these people belong together, and then we compute the mean of some other columns in all these clusters, right? And all of that is done with cross-validation, so it's all fair estimates. You don't want to have your own numbers computed with you in the sample. You want to compute it from other people that are like you. So all these things have to be done just right. And that's what the calculus are good at, otherwise they wouldn't win, right? So that's the whole point, that all these little things are built in just right. Is anybody else having similar results?
Yeah, I finished already.
Okay, perfect. So when this experiment finishes, you'll actually see that it will also build a ensemble. Now you might wonder why 555. So what accuracy 5 does it mean? Well, if you click on the help description right next to the 555 button at the beginning, you can click now, but in the beginning, and you're supposed to enter, there's a help. You click that,
that's really neat.
it explains to you what these settings mean. So 3 accuracy, what does it mean? 7, what does it mean? Roughly speaking, more means we do a little bit more cross-validation, a little bit more genetic algorithm exploration, a little bit more repeats everywhere to make sure that when we say this is a better model, it actually is a better model. So more conservative, a little bit more time-consuming. So even though you turn up the accuracy, not the time, it will still take longer. So that's not how long it will take, the time. The time is a relative time, okay? So the accuracy makes it take longer. Obviously, we know that, right? You can't have all high accuracy and fast, everything. No. It's high accuracy means it will take longer. Time is just a relative time. And I suggest always using time equals 10 and then stopping myself, because you can press the finish button at any time. That's the same as if you had set time equals 2 or 3 or something. Except that time 2 means 20 iterations, 3 means 30 iterations. If you manually stop at 17, there was no knob for that, right? So you're not going to get repeatable results if you manually stop. That's why we have this setting, so you can say, oh, I always want to run overnight with like 3 time. That's the amount of time I can tolerate. So it's more like your time tolerance given a certain accuracy. Now the interpretability knob is not yet well exploited. We haven't done too many things. We have monotonicity constraints in GBM, but not, unfortunately, on the GPU implementation. So it's not really enabled. We have no linear models. That would be a very interpretable model, but that's all coming. So these will be new recipes that you'll see in the new year, where certain interpretability settings will mean actual different models. And then you can focus more on feature engineering, less on model tuning, for example. So now that it's done, you'll see a bunch of buttons here. So you can either interpret this model, I'll do that in a second. You can score on another data set, which means give me predictions of credit card default probabilities for each individual person in that data set. And that will come back as a download. And you can transform the data set. You give your data, and back comes the munched one with all these features that we consider important here. You can also get the training data set out of fold predictions. Now, who knows what that is good for? Yes, you can do more model training with those out-of-fold predictions. You can build a meta model on top of it. That's called an ensemble, right? A stacking model, for example. So you can have, this could be one model. This whole black box could be one model, and it makes a prediction on both training and testing. And that's a new feature. You do this 10 times in a row, you get 10 columns. You throw another model on top, and it says, oh, these 10 columns, what do I do for each individual? Suddenly that becomes powerful. You do this with different loss functions in a for loop. You have 50 columns. You take a neural net on top, those 50 columns, you win CAG, basically. So it's not that hard. You can get the test predictions, that's what you want, usually, and then you can also just get the transformed training and test data sets. Basically, it's all there, right? We have logs, you can download the scoring package. The scoring package has both client-server, HTTP, JSON, RPC, Thrift, everything in there, but also local load scoring. So if you have a Linux system, you will make a Pi virtual environment and run all the there's examples in it that are random data auto-generated with the same schema as this data set.
Why?
I can show that to you. Scoring package here. Oh, it's 80 megabytes. See, that's the whole transformers plus the whole models and the ensemble, everything is in it. So if that finishes, I'll open it later. It's a bit slow right now. And on the bottom right, you see the summary of the experiments here. So you see it was a data set with 24,000 rows. We predicted a certain column. And this was the recipe. It did one internal holdout. And it computed the scores on that one internal holdout. So it split the data one time.
Wow.
And you computed the score on that split. But not just one time, many times. It gave you a good estimate. It made 1,367 features. Who else has more features than me? Anybody has more? Who has less? Should be about even, right? Okay. Perfect. So we have some kind of distribution of features tested. So if you add this all up, you'll have probably 20,000 or 100,000 features tested just now. It's pretty cool. And who has a better score on the test set than 0.404? Less than 0.404, anyone? Okay, that's the power of luck, I guess. Awesome. So you see here the iteration one model in the training holdout was 43.4, and at the end it was 43.0. So not a huge improvement, only 4,000 improvement in log loss. But it's a small data set, we only ran it shortly. This data set is not very easy to squeeze information out, only 16,000 rows, right? Once you see it, you're done. Even the very first model is pretty good already. So it's not just a measure of how well does it improve, but how good is it at the beginning. That's the real judgment. And if you say, oh, my model is way better, then you shouldn't just think that it's better because it was better on your one holdout set or maybe your training metric or whatever. You have to be very careful that the estimate is a good estimate. So this iteration, one estimate that I highlighted there is already a very well estimated number after we do the very smart feature engineering of target encoding already on the categoricals. Already handle missing values, already do all kinds of stuff with the transformation of the response if necessary. So it's not like a dummy model. It's not like the poor man's model first baseline. We don't have a recipe for that. People are asking, they say, we want to see how my model would have done, or what would the random forest have done. We don't show that right now. We show only good stuff, basically. But even the good stuff can improve if the genetic algorithm builds better feature transformers that are useful. Good question came up from the audience. Why does it jump at the end? Why does it fall down so much? Well, let's stack it. That's the final model here that took 96 seconds, and there was 9 models trained. So it's 8 models and a final meta model. The 8 models are 2 different parameters, each 4-fold validation, and then they make 8 different predictions on the test set. And then the meta model puts them together. So this is already, it's in this case, it's actually blending with a linear blending. So each of the 2 components have a weight. and then they get put together. It's not half-half, it's whatever the linear blender gives right. We're not doing proper stacking right now, but that could be another recipe with neural net or extra trees or something here, depending on what customers are asking. But I'm sure they're asking for higher accuracy and resolution. So that's basically it, except that we haven't done the experimentation mode and the interpretability, and we have Patrick Hall here, who authored the whole brains behind it. And if you have a microphone, I would really love for both Mark and Patrick to give a quick 2-minute summary of their work and their findings about it. Can we make that microphone live here? Good question. When you say finish, it will jump to the end and then do the ensembling and the deployment packages. So we'll always get the deployable model that's pretty accurate. You're just saying, I'm happy with the feature engineering so far. And you never know what's coming next. At any point in time, it could jump a lot. You don't know. That's the feature engineering for you. Unless you have like a base limit of what's in the data or something. Do we have a mic? Otherwise, I think you guys have to stand here.
We're going to let them do just a few quick minutes. I know some of you really had a lot of trouble with Quick Labs, but you can use that key later on when you're at home. And I know that we have a lot of questions, so I told Patrick and Mark they have to talk very fast and a few minutes so we can get to some of the questions really quickly, okay?
Hi. So I'm Patrick, and actually Navdeep, Gil, and Mark Chan, who are around, we'll be doing an hour-long hands-on just on this tomorrow. So I think that's the biggest take-home is tomorrow afternoon we'll be focusing just on the interpretability aspect. So if you're interested in that, please check it out. Just very briefly, our goal here is to be able to justify every decision that this black box machine learning model makes, so that we can show which features contributed to each decision that the model made, and to a certain extent, how much each feature contributed to that decision. And we do go so far as to attempt to write them out in plain English. So here we're saying something, so specifically for this person, we're saying something like their most recent payment status, pay underbar 0, was 2 months late, and that resulted in their probability of default increasing by about 35%. Okay? So we're trying to assign local variable importance for every single decision that the model makes, so that from that we can build reason codes about why the black box model is behaving the way it's behaving. And with that, I think I'll leave it off. I'll sort of give you guys that teaser for tomorrow. Come see it tomorrow afternoon if you're more interested in the interpretability stuff. And I'll reiterate, if Quick Labs didn't work for you, the key that you got in the instructions, you can download an evaluation copy and try it later, and that key should work for you.
Yes, the best way is to get a key from our website. That way it's longer lasting. It's a proper key. This is more like a toy key for this instruction here, but both will work for a few days or so. But the other one is the one that will long term be with you. So get the one from your official request on the website.
I'll also be trying out quick. Similarly, tomorrow I'm doing something that really kind of looks at these features, comparing some actual models I built. So I took my own effort without driverless, and then ran it with driverless, and once did both at the same time. So tomorrow, 2-ish, 2:30, something like that, I'll be doing something about that. So you can check that out, where we start digging into some of these descriptions you see here. If you hover over it, you see a really nice description. We'll work to improve that, but already is really nice to me. It may take a little bit of getting used to some of the lingo that is in there, and the documentation will actually help you. The documentation is really good if you can read what target encoding is. There's some powerful things in there that, while you're using driverless, we may assume you know, so we'll at least tell you what we're doing. The docs will help you if you need to get up to speed with some of that. So tomorrow, we'll take a couple problems and tear those apart, look at the top features that are created, and show that it actually tracks pretty well with some interesting concepts that I did myself. I look at a problem, shift it around a little bit, and I was actually kind of impressed with what Driverless was doing with some complex interactions. The other one thing is that I found it to be very stable, and it improves as we've done some. I ran one a couple days ago where I had not put in a time series, and it was very overfit. I got an inaccurate loss coming out of the screen, and I come to check in with 1.09, not even today's 110, but I thought everything was worse. But actually what it had done is it had done the proper thing. So we've encoded some pretty interesting stuff in there. Dimitri spent a lot of time on stability of these, and I found that that really works, especially for IID data sets. But now we're adding some time holdout methods so that even if you don't know what your data set is, but we detect that it is, we're going to help you build the right model, which is something that I'm personally passionate about. So do a little more about that tomorrow. So it sounds like we had a lot of questions, so I'm sure that we've got much of the best format. We have about a minute 50 left, but
Okay, there's a question about the different components. So H2O GPU is a core piece to the driverless AI because we're using GPUs, right? So there's XGBoost, there's truncated SVDs, there's clustering, logistic regression, linear regression, all these models that all implement on GPUs now. And we are putting those into driverless so that everything runs a little bit faster. Deep water is more or less deprecated, as Sri said, so we're not really supporting it. If you want to do deep learning, we propose you use Keras or something like from Python where you're more expressive. If you want to just start and play with it, you're welcome to use H2O's deep water, which does have GPU support. But we're not really using Java to call TensorFlow C++, right? We can just call it from Python if we need to. So we will have TensorFlow in the product.
there was a question on there where we can see what the transformations are. Are they just linear? And no, they're not. So that's, if you, again, if the middle section right below the knob that's telling you how percent complete, there's that feature importance. If you hover over each of those feature importance, you'll see that description again with the docs. So these are not trivial transformations. They're really good. There's some complex interactions going on. So yes, we do tell you that. And like Arno showed, we didn't quite download it, but you can actually download a data set that shows you the results of those transformations on both your training set and your testing set if you've provided them. So those are both important pieces of getting this done. And the system does tell you the output, and it tries to describe to you what it did.
So there's a file called features.txt that you get in this coding package that explains all the features. There's names of the feature columns and then explains them in plain English. And there's also a variable importance column, so you can see which column is how important. Some of them are zeros. That's because they're still included, even though they're not necessarily picked up by that one final GVM model. But it's maybe picked up by the ensemble. So we're not dropping all the columns, so don't be scared if there's a zero sometimes. It's also an artifact of the genetic algorithm. We're bringing in all individual with a lot of genes in them, like a human, but not all genes are active and necessary. If you cut out a little gene somewhere, you're not gonna just die, right? Basically. So the point is that these genomes, they're mutating and all that, not all the pieces in there are 100% necessary, but the individual that's the best in the end has a lot of good stuff. That's kind of how you should think. This is the package, the scoring package, and you can look at it yourself, but it's all Python code, it's easy to go through, and basically download it, play with it, that's the takeaway message, and thanks for your attention.